So let's begin our review of the gravimetric analysis of carbonates, the calculations, and the possible errors in this lab. So real quickly again, what we did is we took an unknown metal carbonate, we dissolved it in water. Before we did so, of course, we took its mass, we took its grams, okay? And we did so for a reason, because we know that we were going to try to find whether or not this metal Group 1 carbonate was either lithium, sodium, or potassium carbonate. And because it was one of those three, we knew their formula masses. And we know the formula mass is equal to the grams per mole. And so what we were trying to do was calculate the experimental formula mass for the unknown salt. And because it's grams per mole, that's what we're after here. So real quickly, what we did was we massed out our sample, not knowing if it was one of the three. We dissolved it in some water. The amount of water wasn't important because it was about the number of particles here. And then we did is we added some excess calcium chloride solution. And both of these are soluble based upon the solubility rules. And when we dissolve these ions into the same solution, a precipitate occurred. That precipitate, of course, is calcium carbonate. The -2 ion here strongly attracted the +2 ion. Based on Coulomb's law, when the size of the charges increase, so does the attractive forces. So much so that water couldn't compete for those charges and dissolve them. All right, so we made calcium carbonate precipitate, and we'll write it here. And we knew that chemical formula. And remember, this is a gravimetric analysis, meaning we're going to use the mass of something we collect to analyze something that we start with. Also, we can call this a gravimetric titration and or precipitation analysis. So we're going to precipitate out this important carbonate that came from the original ion. And I guess I could write that in blue to keep that nice and color coordinated because I am so stylish. So there we are. And that's our solid. And so our next step was to collect that on a filter paper. Okay, however you want to do that. Of course, you mass out the filter paper, and of course, we dry. All right, and after we dry, we mass the filter paper and the calcium carbonate, which is chalk. Again, we subtract out the filter paper, and we should have the grams of our calcium carbonate. All right, keeping our color coordination. Why not? Okay, so what I'm going to do is use sample A from my virtual lab that I made, and what I got, okay, was 1.36 grams was my original mass of my unknown sample. All right, and what we're after to get our formula mass, grams per mole, is the moles of the sample. All we need to know is the moles of our sample, and we've got an experimental formula mass that we can start analyzing to see what, in fact, was that white salt. And that's, of course, the analysis part here. Now, when I massed out my calcium carbonate, okay, the grams of calcium carbonate after I subtracted out the filter paper was approximately 1.18 grams of calcium carbonate. All right, and so that's essentially what I got. So we dried out the calcium carbonate, we massed out the, of course, calcium carbonate and its filter paper. We subtracted out the filter paper, and now I have my grams of my chalk or my calcium carbonate. And that's my experimental value. Okay, let's mark that there. Now I say experimental because we got it in the experiment, and of course in all experiments there are what? Flaws, procedural flaws, limitations, errors, all the above. So now the next step here is to understand how many grams, or in this case, how many moles of calcium carbonate that we have here, because that's where the precipitation or the gravimetric analysis is here. Knowing how many of these formulas will tell me how many of these carbonate ions will tell me how many carbonate ions are in the solution and eventually how many carbonate ions are in the original formula. So let's do that, okay? And I'm gonna write this, okay, right here. So I'm gonna take my 1.18 grams of my calcium carbonate, and I'm gonna convert to moles. All right, and so grams equals 1 mole. I like calcium carbonate because the formula mass of calcium carbonate is 100 grams. If you take your calcium plus your carbon and 3 times your oxygens, you get approximately 100 grams. And I'm rounding here, okay? I think that would suffice here. So grams, your professor may want you to use your atomic masses out to hundreds or thousands place. I'm gonna have my students round to the nearest gram here. Okay, so I want to go find those moles because that's the value that's going to go there. How do I get moles of calcium carbonate to moles of my original solution? Well, that's what's going to happen here. Okay, and I'll show you why it's the same thing. Because I'm going to get rid of calcium carbonate. And if you look with me, calcium carbonate, for every 1 calcium carbonate, how many carbonate ions are there? Hey, there's 1. In one of these formulas, there is 1 blue carbonate ion. All right, next step. What do we have? Well, we know that the calcium carbonate has just been canceled, and so essentially all of the carbonate ions that were in solution got locked up into this calcium carbonate. So the moles of the calcium carbonate, that's a how many number, equals how many free carbonate ions were in solution. And because we know that 1 calcium hit every carbonate, that's why we can make the leap from the moles of the calcium carbonate to the free moles of the ions. And all of these carbonate ions came from the M2CO3. And this is the next leap here stoichiometrically. And again, people can see it. Since there's only 1 carbonate in this entire formula, then we know that the moles of the free carbonate ions has to be the moles of the original formula. It's a 1-to-1 relationship, and you can write it here. So we have moles of carbonate ions. Let's get rid of carbonate ions. 1 carbonate ion, CO3 negative 2, is equal to 1 group 1 M2CO3. Okay, and then I can cancel my heart away here. And so you can see that from the grams of the calcium carbonate, all right, and I'll just write this away, I've got what? Calcium carbonate, there's 1 carbonate. For every 1 carbonate, there's 1 M2CO3. I've got moles of my original compound. That is the precipitation or gravimetric analysis or titration. That's the link. The link was precipitating out that important ion and that relationship. Now, because I have 1-to-1-to-1, don't always think that in other problems that you do this, it will be 1-to-1. In this case, there was 1 carbonate for one of these formulas. And in this case, there was 1 carbonate for that formula. That may not be the case, and you may have to adjust these numbers accordingly. Don't be a robot, okay, and do these problems exactly the same way because you saw it given to you this way. So let's go find those moles. Okay, we take our calculator, okay, and we do that. And so we get 1.18, and we divide by 100, and we times 1, divide by 1, times 1, divide by 1, and what you get is 0.0118. And I did not need my calculator to do that since I'm dividing by 100, but I used it anyway. So what I got was the moles of my original compound from this precipitation analysis, from using the ratios, right? That's what stoichiometry is 0.0118 moles. Okay, let's go find our formula mass. Okay, and so this one I do need my calculator. I can't do this one in my head. 1.36 divided by 0.0118, and what I get is 115.3. And since I have 3 sig figs, I'm going to round that to 3. So 115, and the units are grams per mole. Okay? And that, my friends, is your formula mass. Your experimental formula mass. Now the question is, what salt is it? Remember I said to you that we either had one of three salts. We had lithium carbonate, or we had sodium carbonate, washing soda, or we had potassium carbonate. All right, and knowing their formula masses, okay, we can identify what their values are. Okay, we know the formula mass of lithium carbonate. Well, there's 2 times 7, 14, plus 12, plus 48, right? 48 is 3 times 16. I'm rounding off here. So 8 and 4 is 10 is 14, and we have 74. 74, if I do that correct, 8, 2, 10, yep, 14, 4 and 2, 6. I have 74 grams per mole. Oh, there's something on there. That bugs me. So 74 grams per mole. I think I want this one. All right, so that's 74. Okay, and for speed purposes, this is 106 grams per mole. And this, I believe, is 138 grams per mole. So those are my formula masses. And so you say, okay, Mr. Grotsky, how do I know which one it is? Because we got a 115. It appears to be in the middle here. So it appears that I don't have lithium carbonate, but I'm in between. A lot of people will say pick the nearest one, but I don't know if that's the best method. So where am I in this process? Well, I have a formula mass that's a little bit over the 106 that I expect for the sodium carbonate, and it's a little bit what? A little bit under the K2CO3. Should I subtract these numbers and see which one it's closest to? I don't think so. I think there's a better way to do this and better way to think about this, and I'm going to give you 2 ways. Okay, number 1. All right, let's think about, we're going to talk more about all the errors at the end of this, but I want to talk first about what's a major error. Now, when we precipitated out the calcium chloride, okay, we filtered out and tried to collect all of the precipitate, all of the solid that appeared in this ionic crystal that developed. That is very challenging to get every single piece of precipitate. And then if we did, okay, the transfer of the precipitate to and from the oven and the scale could result in loss of the precipitate as well. There's no doubt in my mind, one of the limiting factors in this type of procedure where we're collecting a precipitate is that we don't get it all out of the solution. We could have left some of it in the beaker behind. I know we were trying to wash out the beaker. We were also trying to wash off the stirring rods and everything else, but inevitably there's going to be some precipitate that we don't collect, all right? And it's very difficult to get all of it. So the limiting part of this procedure is that this mass of calcium carbonate is an undervalued result. It should be bigger. We had to lose something or didn't collect it all in the filter paper. All right, so I know that this is definitely going to be smaller than it should be. And that's the important key here, is that our percent yield should be under 100. We should have lost some. We should not be way over if we control for the other errors, and I'll speak to that in a second. With that being said, knowing that probably my major error here is the loss of some precipitate, either in not collecting it all or in the transfer back and forth, what does it do is it makes my calcium carbonate number get undervalued. And if I have a lower undervalued, okay, result because of the loss of some precipitate and not collecting it, I'm going to have a mole value that's undervalued. And if this number is smaller than it should be, hey, if the denominator is smaller, the whole result, okay, is an overvalued result, which means my 115 is bigger than it's supposed to be because this number for grams is smaller than it's supposed to be, which would make me solve for a smaller mole than I'm supposed to have. And because it's in the denominator, making the denominator smaller makes the whole value larger. So my 115 is elevated than it's supposed to be. Notice 115 is above 106. So this screams to me that I probably have sodium carbonate. Okay? Because my 115 is an overvalued result. I'm over the 106. So measuring which one is closest is not, my opinion, the best way. It's looking at which one you're over. And again, it probably works out that this is a little bit closer, okay? And if I lost and I was sloppy in my lab and I was lazy and I didn't grab a lot of the precipitates, I didn't refilter out, and one of the two I didn't refilter out twice, okay? Or I spilled some, this result will be even farther away. So it's going to be, in my opinion, the salt that you have is going to have a molecular mass that's going to be greater than the one. So it should be above, but below the next one, okay? But if you're not liking that, we can do some math, in my opinion, to support that. So let's go to the percent yield calculation. We're going to figure out, here we have our experimental value of our calcium carbonate. We think it's undervalued. Now, by my analysis here, if you can follow me, I think that sample A was sodium carbonate from the major error here. Let's see if that's supported by my percent yield for this compound. What I mean by that is, let's do a stoichiometry problem and solve for exactly how much calcium carbonate I should make given exactly 1.36 grams of my, now it's not magnesium, I'm sorry, it's not M2CO3, I'm saying it's Na2CO3, and these M's are Na. That's what I'm saying now. Okay, so let's do that math. Okay, let's do that right here. I'm gonna move this to the side. Not much movement I can do here, but I'm gonna rewrite it so I have some room here. So I have 1.36 grams of my original salt that I now think is sodium carbonate, and I solve for the moles of my sodium carbonate through the moles of the calcium carbonate that we just talked about, and I'll keep my color coordination here. All right, 115. As I said before, I think it's an overvalued result because this number, okay? I'm gonna get rid of that now so I can do this stoich problem. Okay, and we're gonna do two of them to verify if in fact I have sodium carbonate. So I'm gonna start with 1.36. Again, what I'm doing is I'm going to assume it's sodium carbonate, and what I'm gonna do is I'm gonna solve for how many grams of my precipitate I should have. Okay, so first step, let's write what we have here. We're going to say it's sodium carbonate. Okay, next step. All right, next step is I'm going to get rid of grams. All right, and for every, I have to go to moles because I'm going to use the mole ratios here to solve for that. All right, moles, what do we say, 106 grams? Okay, did a formula mass, and now we need to know the ratios, okay? Now, how do I know the ratios? Well, we need to have a balanced chemical reaction, right? Let's do the net ion reaction. As we can see, one calcium, okay, goes to one carbonate, okay? And so that net ion reaction that we're gonna use to balance is very simple, okay? We have, what, 1 calcium plus 2, aqueous, plus 1 carbonate, negative 2. Of course, it makes what? 1 calcium carbonate, which is a solid, a precipitate. Charges go bye-bye. You don't write them in the precipitate because it's a salt that's electrically neutral. Okay, and so there's a 1 to 1 to, I'll just put that 1 right here, 1 ratio. The ratios are 1 to 1. Be careful here, okay? In this case, there's 1 carbonate for 2 sodiums, but the sodiums are not important, okay? So the moles of the sodium carbonate are the moles of the carbonate. And if you don't see that, we can put that ratio right here and keep yourself organized. Hey, for 1 Na2CO3, there's 1 what? CO3 negative 2. Now that may seem silly to do, but there are going to be problems you see where it's not 1-to-1. So it's really important. There may be 2 carbonates for different other salts that you may encounter in other problems. Don't be a robot, right? Okay, so we know that we're going to cancel out that, and we have our carbonates. And what do we know? There's 1 carbonate to 1 calcium, okay, or 1 calcium carbonate. So we can put that ratio there too if you want to. 1 carbonate to 1 calcium carbonate, CO3. All right? And again, this is exactly what the precipitation analysis does as well. And now we have moles of calcium carbonate, and we want to convert this to grams. So party people, we know that 1 mole's up top here. I'm using my units. We want grams. The formula mass of calcium carbonate is approximately 100 grams. That's good enough for me. And my moles cancel, and I'm left with that value there. Okay? And so I put this into my calculator, and I got 1.36 divide by 106 times 1, divide by 1, times 1, divide by 1. Okay? And of course, times 100. And what I get is 1.28. 1.28. That's what this value is. 1.28. All right, I'm going to write that here. 1.28. 1.28 what? Grams of calcium carbonate. All right, party people. That's exactly how much I should have made in calcium carbonate, assuming I had 100% 1.36 sodium carbonate, and there were no errors I did not get, or in this case, assuming I got all the precipitate out of the solution, and of course, assuming I didn't spill any. What did we find? 1.18. Experimentally, we gathered 1.18 in that lab, which means what? We are under what we expect. That makes sense to me. And if we do a percent error, do a percent yield, all right, percent yield, we're going to take our experimental 1.18 grams divided by the stoichiometric value we got by doing our pencil and paper math and using ratios and mole concepts, right? 1.28. Hey, we're under by a little bit. That makes sense for me, okay? And this is really, to me, telling me that, boy, I bet I have sodium carbonate. Percent yield. And what's important to me is that really speaks to the fact that I have sodium carbonate. I was under what I expected because I know it's hard to grab all that precipitate. I could have lost some in the transfer, kept some as I'm moving it from the filter paper to the watch glass, and moving the watch glass from the oven back to the scale. Okay, we're not missing an incredible amount, but 0.128, we're missing 10 100ths. I mean, that's small of a gram. But in any case, there it is. Now, what if I thought it was potassium carbonate? What if I thought it was potassium carbonate? What if this was K2? Let's adjust this and see what we get. And this is really important. If you thought it was K2 because you may have thought, well, it's in between and it could be potassium carbonate, let me show you how I think this math would not support that result based upon knowing what our major error here is. So let's take this, okay, 106, and now let's change it to 138. All right? And if I do that, let's go find our new result, okay? So 1.36, and why is this 138? Well, potassium is a more massive, heavier atom. So if you divide the same, and by the way, this will be now K, right, 2. Same value here, you're going to get less moles. But in any case, 1.36 divide by 1.38, okay? And you get 0.98 moles, and you get times that by 100, and I know I can do that. And so I get something close to 99 grams, okay? And 99 grams, I'm sorry, I get something that's times by 100, I'm sorry, I get 0.99 grams. So when I do this math, I now get, and I'm put this in red now because this is wrong, right? Red's always wrong, and I dropped my marker, sorry. Okay, so when I put this in as 0.99 grams, well, this becomes 0.99. Oh my gosh, you can clearly see experimentally you have more than is theoretically possible. Your percent yield is going to be way above 100. That doesn't support this lab, assuming we had a dried compound. All right, so that percent yield, if we were to do it, okay, it would be 100. So if you got your compound with a percent yield that's way above 100, okay, it's hard for me to support that through your analysis that you have the right chemical. Divide by 0.99, okay? And I get approximately 119% yield if we change this to K, okay, and change those values. So that does not support. All right. So in any case, let's go back and talk more about these errors, okay, that could affect this lab. And I want to finish this off this way. All right, so we know that we definitely have established that sodium carbonate is my compound. Okay, let's talk about some other errors. All right, number one, let's talk about the fact what the major player here is our molecular mass. And we know that molecular mass was due to, okay, the grams that we got. In this case, it was 1.36. That's what we measured over the 0.0118 moles. All right? Now, that is what we're looking at here. Okay? Now, let's make that clearer. All right? And that's not doing it. Keep grabbing the wrong one, party people. Help me out. Okay. So this is our major player here in trying to decide whether or not, what kind of major errors we have here. Okay? All right, so this is mole. So this is the major one. I'm sorry for, I'm getting OCD on that. Now, so if this is our value, and by the way, as we talked about, the percent yield and percent error is based on the calcium carbonate you're supposed to make, not on this value, although this value helps us determine. So here's our errors. First and foremost, okay, we already talked about the limiting problem. The major error, in my opinion, okay, is that the moles are undervalued, which makes this value of the formula mass go up. That's the major error here, okay? We already talked about that. But what are some other errors? Well, number one, let's look at the numerator, 1.36. There's no possible way, no matter how much money I spend, that these chemicals are 100% what they say they are. There has to be some impurities, okay? If there's 0% impurities, these things would be $10,000 per bottle, okay? It's just impossible for us to afford that, or even for the companies to actually make them. So there are some impurities. The question is, what do those impurities do in terms of precipitates? Are they adding or not? So there's some leeway here, but let's just pretend it's an inert precipitate that doesn't, it's an inert chemical that's mixed in, and it doesn't precipitate. Oh, we don't know for sure, but we can make that guess. That means that this value is a what? Is overestimated a little bit, right? Meaning you're saying it's 1.36, but it's an overestimation because some of that is another chemical that's an impurity that's not precipitating. Now, of course, that's we don't know for sure. So if this is an overestimation, hey, that brings this value what? Up a little bit, Now, what if it is a chemical that does precipitate with the calcium? Well, then it would bring it down a little bit. But I'm telling you that these things are assayed right around 99%. So these things are pretty pure. So at 99%, those errors are small and minuscule, but they can go either way. We don't know for sure. All right. Now, something else to think about, another major player here, is that we had to filter out the calcium carbonate on the filter paper. Okay, now the filter paper, did we verify like we did on the hydrate labs using crucibles when in fact all the water was driven off? No, we didn't. I just heated this for a long period of time. What if there was some water left? What if I did not drive off all the water? Because we didn't verify. We didn't do what? Heat it, mass it, heat it, and mass it until the mass stayed constant to verify all the water was lost. So we could have some water here contributing to the mass, which means possibly the mass of my calcium carbonate is a little bit bigger, okay, than it's supposed to be. I know we said down, but you could have a scenario where I didn't dry it off. So having water, okay, still on the precipitate and or in the filter paper would, in this case, drive this number up a little bit, which would drive this down a little bit, okay? So there's some competing errors here to discuss, okay? So if I had some water here, this would give me an overestimate of the grams, which would make my moles bigger and this lower, okay? So there's some competition here. Also something that we can think about. Did we wash off our precipitate? Because we know that we had these spectator ions. And these spectator ions, as you dry, will crystallize on top of this. So we could have had sodium chloride crystals on top. As if I had this filtrate that had these free ions, and if we didn't wash off with distilled water our precipitate, okay, as I probably did not in the video, all right, as it dried, as the water leave, the sodium chloride would come together, and you would have at the end of the day sodium chloride crystals on top of that, which would also be a what? Another competing error against the loss of the precipitate. That would do what to the grams? It would make it heavier, okay? Subtracting out the filter paper, okay, you're gonna have a larger difference because you're adding more mass, and that would drive this moles up and this down as well. So those are all things to think about, okay? I will tell you that I did dry these very, very well. For those classes that had it overnight, it was dried overnight. There was one class that I heated it during a 20-minute period using the microwave. And in the microwave, there was some splatter, loss of the precipitate. And I was trying to get it done for that one period, so that could have been a case where there was still some, of course, some water there, but something to think about. So a lot of competition of errors here, but the major player for me is, I would think, is the fact that you couldn't get all the precipitate. And since it's 100 grams per mole, anything missing, you really missed a lot of weight there. Water is 18 grams per mole, so if you had some extra water on there, obviously if it's wet, it's gonna be a huge, huge addition of mass and a huge over-evaluation of your grams and thus moles. So something to think about. Hope that helped, okay? But certainly a good discussion of errors here. But I love the percent yield with the idea that it's almost impossible to get all of our, all of our mass of our carbonate. Assuming that we did dry it out, okay? That's a major player here. And for the most part, they look pretty dried, even though I didn't verify. So I hope that helped. Now, there's one more cool piece to this lab that I want to talk about, and that is the following, that if you were to examine the two containers and their crystalline structure of the two salts that I gave you, A and B, which were either potassium or sodium carbonate, you can physically see the differences in the size of the crystals and get a feeling for how and why one might be bigger than the other. So it's kind of cool. So what I'm going to do here is put up the crystals, and this is crystal A, okay? So this is what we had in the video. Okay, I don't know if you can see some crystals here, but I'll move that over. And so there are some crystals right there. All right. And then we'll go to the other solid. And this is B. I don't know if it's coming into the frame, but here are some crystal B's here. Just going to move them over. And if you can I don't know if you can clearly see, but, all right. So what's really neat is looking at the microscopic world, so to speak, although we're not really. This is the size, this is sample B over here. Look at the size of these individual kind of pieces of crystal. And look at the size of these. These are much smaller pieces. And if I can maybe, okay, get the best I can get, it should be clear to you that B, which is to the left, to the right here, these crystals are physically bigger than the crystals here. So these are the potassium carbonate. These are potassium carbonate, and these small little crystals are the sodium. And you may say, well, why possibly? Well, maybe it's because the potassium is a much, much bigger ion than the sodium. So you can actually open these up and pour to see what you had, okay, which is pretty cool to look at. We were looking at the gravimetric analysis, but we can also look at the size of the crystals that give us some hints about what we had. So in sample A, we had these smaller crystals, and they were made of sodium ions and carbonate ions, and these sodium ions are smaller, and that may have led to the smaller and finer amount of salt crystals here than the larger ones here that are made of the potassium. Kind of cool, I think.